Okay, welcome back, class. We are starting week 5 of the semester. For this week, you're going to want to go ahead and look over read chapters 5 and 6. That's going to pertain to this week's online lectures. There will also be a discussion topic, which is going to be a sun angle equation, where you're going to complete an equation, you're going to create your own, and then you're going to solve a classmate's equation that they have created. And then you're also going to take a quiz this week. Remember that these quizzes are 5 questions. And I want you to keep working on the Mount Kenya paper. Remember that this is a paper that's supposed to identify the scientific method. You're going to be pulling out key terms that are new to you. And you're going to be answering some questions on the findings of this particular study. The fact that a lot of the terminology is new is great because it shows that this is a learning opportunity for new ideas and concepts. So that's what I want you guys to make sure that you get started with this writing assignment because it's due February 20th. Okay, so before we move forward on the Earth-Sun relationship and talking about atmosphere, I want to go ahead and review latitude. Last week I submitted latitude and longitude and had you guys identify issues within the degrees, minutes, and seconds. Everyone did a great job, but just a little bit of review on latitude. Remember that these lines of latitudes are called parallel lines, and the equator, which is 0 degrees, divides the Earth into the northern hemisphere and the southern hemisphere. So when we see a latitude, we always see a north or a south associated with that coordinate. So northern hemisphere and southern hemisphere. We know that the latitude lines are an angular distance that's calculated from the center of the Earth, measured outwards. So as we see here from the equatorial plane, we have an angular distance of 49 degrees, and that represents 49 degrees of latitude on the Earth's surface. We also have significant lines of latitudes that we will be talking about more, especially when we talk about weather systems and global circulation patterns. These lines of latitude we identify, so areas such as the low latitudes, we identify this as being in the tropics from 23.5 degrees north to 23.5 degrees south. So that's going to be the range of latitude in which you see, as we identify as the low latitudes, equatorial tropics, and subtropics. We have mid-latitudes, which is going to be the latitude where we are located at, between 35 degrees north and 55 degrees north, and also in the southern hemisphere as well. And then we have our high latitudes, which we identify as our Arctic and subarctic, going from 66.5 degrees north to the North Pole, and 55 degrees north to 66.5 degrees north for the subarctic. And the same can be delineated in the southern hemisphere. Now longitude. Now last week we watched a movie about longitude, and you guys had some great responses about why longitude took so long for geographers to be able to come up with a clock small enough that could accurately record time. Longitude is a measurement of time, and one can say that longitude is an arbitrary line that was pretty much discovered by geographers and astronomers in a way to break up the Earth in a coordinate system to match with our latitude. So able to break up the northern and southern hemisphere and also the western and eastern to be able to describe a point on the Earth's surface. But this is all review. So oftentimes when we are talking about lines of latitude and lines of longitude, there's a terminology that we use that is identified as a great circle versus a small circle. Now, a small circle is not going to equally divide the Earth in half that we see in figure C at the bottom there. And so a plane that intersects the globe along a small circle splits the globe into unequal sections. So you could say that the higher lines of latitude are small circles, but one line of latitude that equally splits the Earth into half, into the northern and southern hemisphere, is going to be our equator. And so the equator is a great circle. You could also go ahead and go further in discussing about lines of longitude. Now, every line of longitude, if you were to follow one line of longitude all the way around the globe, that would equally dissect the Earth into two equal halves. And so we could say that every line of longitude is long and therefore a great circle. So just kind of a nice rule of thumb in review of these two lines. Okay, so now we're going to move into Earth's early atmosphere and the location of Earth. We're going to talk about the orbit of the Earth and tilt. And then we're going to move into seasons. My son right now is completely obsessed with Earth and space and dinosaurs. And so the fact that, the Earth is described as a Goldilocks planet or a Goldilocks planet, and the fact that it is located at a very strategic location in the universe where it's not too hot, not too cold. We're able to have an environment that has an atmosphere. That atmosphere protects us from harmful radiation that's coming from the sun. And we know that the sun is a medium-sized star, and that sun is constantly giving off energy, and that energy is derived from nuclear fission of hydrogen and helium. And we know that the sun also has radiation that is released that is often described as solar winds. And we know that solar winds are charged particles that are emitted from the sun. And when that solar wind it comes in contact with the outer layers of our atmosphere, we have a phenomenon called the northern lights that are created, or also known as the Aurora Borealis or the Australis in the southern hemisphere. And when we see this reaction taking place, we know that it's the solar wind that's coming in contact with our ionosphere. And our outer layers of our atmosphere protect us from these harmful waves. So we have a lot to be thankful for our solar system and for our layers of the atmosphere, which we'll get into in much more detail. So as we start talking about the composition of the atmosphere, we're going to be using terminology such as the homosphere and the heterosphere to determine compositions of the atmosphere at certain levels. So the homosphere is going to be the lower level of the atmosphere, and we can see that it is made up primarily of nitrogen at 78%, oxygen at rounding up to 21%. We have our carbon dioxide, our argon, and trace gases. Now these are the current distribution of gases that we see in the homosphere to date. Now we know that the early atmosphere was not very hospitable. It was the first atmosphere started to take formation about 4.4 to 4 billion years ago. And it was rich with nitrogen and krypton. It would be something very similar to what we'd see on Venus, so not very hospitable. The second atmosphere started to evolve and having more rich carbon dioxide. Scientists believe that this is from the interaction of volcanic activity, and this is around 4 to 3.3 billion years ago. So our volcanic activity adding condensation nuclei, so dust particles, into the air, and those dust particles are going to attract any type of moisture. So if there's any water vapor available, they're going to come together and collect and form precipitation. At this time, there was also nitrogen, methane, and sulfurous gases. And then we start to see our living atmosphere. So these are kind of the three atmospheres that are identified, the first, second, and then the current one that we have to date. So early atmosphere, as I mentioned before, the scientists believe that oceans and the water for oceans were brought to the Earth by a period of time where the Earth was constantly being bombarded by comets and asteroids and meteors. And so those foreign objects, those space objects, were able to bring in ice, which it would provide us the water vapor. And this would be a lot of meteors that would be hitting the Earth and bringing that water vapor. Another theory is that when this water vapor was brought to Earth, there was also quite a bit of volcanic eruptions that would intensify the water vapor with the condensation nuclei and gases to help accumulate that moisture. So current evidence of early life on Earth took in the formation in the oceans. Then this is in the form of simple cell bacteria and single cell organisms, such as diatoms. Now, to think about what the early atmosphere was like, it makes sense that the first type of life took place in the ocean, because remember that our current atmosphere was not in place. So we still had, harmful radiation from the sun. We still had toxic levels of gases in the atmosphere. And so having a protection of the ocean to filter out those harmful waves of radiation was very important. And so that's why it makes sense that life had originated in the ocean. As we started to have more carbon dioxide and oxygen start to develop, we started to see plants in the ocean, which started to produce more of this oxygen at large quantities. And so over a long period of time, that oxygen started to accumulate in the atmosphere. So we really have a lot to thank for the ocean, for the water vapor and ice being brought to the planet by meteors and volcanic activity. Where we really saw in the geologic period of life taking place in the ocean is identified as the Cambrian explosion, where the atmosphere was very rich with carbon dioxide at this point, and we started to have early sea creatures that had shells that were made of calcium carbonate, which is our CO2. And these are the types of shells that we see, that we are still able to see in fossils. These are our single cell creatures, such as our diatoms, that we mine for and use in various products. But these are going to be, and we'll talk about this when we start talking about limestone, these are going to be the fossils that we see in limestone. Limestone is made up of calcium carbonate. Now, our early atmosphere, when the ozone layer actually began to form, was about 440 million years ago. And up until this time, there was really no life out of the ocean. So it took some time for oxygen to accumulate. And then we started to have plants started to emerge and started to grow excessively because there was so much carbon dioxide. And we saw during this period of time, large forests start to develop, coniferous period in the geologic timeline. And during this time, we started to see swamps and very rich in organic matter. And these swamps, when debris would start to accumulate, would be locations where we would find and mine for coal. The breakdown of the organic products would become compressed and turn into peat, and then also over time with pressure and heat would eventually turn into coal. And we will talk about this at great details later on in this semester. So why do scientists accept the Big Bang Theory? And this is an element in your chapter that you're going to be reading. So if the Big Bang did occur, all of the objects within the universe should be moving away from each other. And with the Hubble telescope in 1929, there's documentation that that the galaxy in our universe is indeed moving away from each other. So a great example of observation, a question and observation, going back to the scientific method. Matter in the universe should also be distributed homogeneously, and we do see that. We know that there's observations from the Hubble telescope that do indicate that matter within the universe has generally a homogeneous distribution. So again, formulating a question, hypothesizing that question, and then observing are great examples that tie into last week's discussion about the scientific method. And then, why do most scientists accept the Big Bang Theory? The third point, if the universe began with a Big Bang, extreme temperatures should have caused 25% of the mass of the universe to become helium. And that's exactly what is observed in the heterosphere. So in the outer layers of the atmosphere, we actually have this proportion of helium. So we have helium. So three great examples that support the Big Bang Theory. I'm going to go ahead and stop this lecture here, and you'll be able to continue on this lecture in the next 15-minute block.